We just finished looking at acceleration due to gravity above the surface of the Earth. Now we're looking at acceleration due to gravity somewhere down the surface of, okay, not Earth, sorry, any planet. A star or a moon, it can be anything. So below that. So we drilled and we are here. So this is our point B as of now. So few things about the planet. It has a radius of R. And we have dug through this layer and this has a depth of D. Okay, this is the scenario. So there are few assumptions that we need to make. The planet is a perfect sphere of radius R. The planet has uniform density rho. We neglect rotation of the planet, no centripetal correction needed. And shell theorem applies to this. So by default, this is an implication actually. A spherical shell of mass exerts zero net gravitational force on a particle located anywhere inside it. So basically, if I happen to draw an imaginary, yeah, I think I can use this. If I keep doing that. So anything above this lines, dotted lines, will not contribute to, will not contribute to the pull, the gravitational pull. Below will contribute, not above ones. So this region will not contribute. So this region will not contribute any pull as per shell theorem, right? Okay, so let's come back. So we are considering, let point B lie at a depth D below the planet's surface. So this is the setup. Now, so first thing is we need to identify the mass that actually contributes to the gravitational pull. First thing is we'll go with identifying relevant mass using the shell theorem. Okay. By shell theorem, what we have is all spherical mass outside radius R minus D basically. So basically this will be R minus D from here to here. Produce this statement we have to make. That's why I'm writing this. Zero net force at point B. That's one thing. Next thing is only the mass inside radius R minus D contributes to gravitational pull. Okay, so the gravitational, what else can I tell? The mass inside. Next is computing the mass of in a sphere. So this is what we are looking at. So basically we need to express the inner sphere mass using density rho. So it's quite simple actually. So mass is given by density into volume, and density of the planet actually. Density of the planet is rho. Okay. Volume is 4 by 3 pi r cube. Done? Then what else? Yeah, that's it. So this is basically your mass. So if you want to express in terms of the entire mass of the planet, so this is mass inner. Let me change the mass inner, because end of it we need to express in terms of the acceleration due to gravity. So same as before. Acceleration due to gravity on the surface, whatever is there over here, g, we need to express that. This is b, and this is acceleration due to gravity on the surface a or g. Yeah, let's just stick to that. So we need to express gb in terms of g. So that being the case, we need to re-express this term inner in terms of mass of the outer. So all I have to do is inner, I can just multiply and divide with r cube. So pi rho 4 by 3 pi r cube will give me the mass of the planet, or whatever you guys want to call it as. And the remaining term is r minus d the whole cube divided by r cube. And finally, g of b will be equal to, so this will be g m, mass of the inner shell divided by r minus d the whole square. So a bit of rearranging, r minus d the whole cube divided by r minus d the whole square divided by r cube. So gm by r cube r minus d to the power of 1. So this is your gb. And again, this entire term is gb is your acceleration due to gravity on the surface of the planet, r minus d. Oh, sorry, this is square. So I need to do square of this and by r. So we have divided by r as well. Okay, yes, a bit of math, but yeah, we have reached. Right? So yeah. Now, there are few cases special cases that we can handle. For d is equal to r, that is, we have dug to the center of the planet. We are at center of the planet. What happens? gb will be equal to 0. So that's one thing. Okay, where else? If d is equal to 0 on the surface of the earth, so r by r, that's one more case. I don't think I want to write that. Simple set of derivations, guys. So again, it's the same thing again and again. When it came to acceleration due to gravity somewhere way above the surface of the planet, there too we express in terms of g, and here too we are expressing in terms of g. So again, it's about a reference point. So say all of this I can convert it to below the Earth's surface, right? So we can understand what happens as and when we dig through the surface of the Earth. Reference being wherever you guys are sitting, that's the reference. So as you can see, the gravitational pull decreases as and when we move away, and again decreases as and when we move down. That's one of the observations. So such small observation you guys have to make, get a feel of the topic. So this also happens with numericals. As in when you do numericals, there is quite a few things that you can imply from it. There's a deeper understanding to numericals, right? Not everything can be told. So that's something you should meditate on, you should think on.